Welcome back again, class, and thank you for joining me for 6.6. So, yesterday we focused on function operations. Today, I'm actually going to introduce you to a brand new operation that we call composite functions. Now, we're going to start off with some basic examples of what a composite function looks like. So, we're always starting the same way as we did yesterday, where I just label out two functions for you. So, in this case, I'm giving you f of x is 3x plus 1, and g of x is x squared plus 2. And this new composition function can take two forms. It can look like this. So f composed of g, 2, or what more commonly I like to use is I think of that as f of g of 2. Because really I think that gets more at logically what you want to be doing. Because here, what you want to do, you want to calculate g of 2. So I'm going to put 2 in for g. So, excuse me, class. So I'm going to put in a 2 to g. So 2 squared plus 2. So 4 plus 2 gives me 6. And now what you're going to do is now you take that 6 and now you put that in for g of 2. Because if g of 2 equals 6, now this just boils down to f of 6. And f of 6, if you plug that in, 3 times 6 plus 1, so 18 plus 1, you get 19. So that's why we call it a composite function, because you end up using both functions. You put it in the first one, take that result, put it in the second one. All right? And that's why I think, again, the second notation makes more sense. All right? Because you can really see, all right, I'm starting with g of 2, taking that, once I calculate that, and now that gives me the f. So I think of working these inside out. Okay? That's one of the big things today, is work from the inside out. Now, something cool that I'm going to show you is that is not the same as if you do it in the reverse order. You're not going to get the same answer. So look at this. This time I'm taking g composed of f of 2. So we have g of f of 2. So again, starting from the inside, I'm going to start with that f of 2. So that's going to give me 6 plus 1, or 7. Now I take that and I plug it in, because if f of 2 is 7, that means really what I'm looking at is g of 7. And g of 7, well, plug that in to the g function. So 7 squared plus 2, 49 plus 2 is 51. So notice, completely different answers if you go in the reverse order. Okay, which is going to be very important, so that you're not getting the same thing. So what's happening here? Well, again, we're working from the inside out. So you evaluate that inside piece first, and then you use that result as the input for G. So here's a little flow chart for you to understand. So we're starting with a domain of F. We're putting something in there that becomes the range of f. Remember, a domain you use as input, the range you get as an output. Well, now that output becomes the new domain of the outer function of the g, which results in an output of the range of g. Okay, so it's kind of a flow chart. The input of 1 becomes an output, but that's the input of the next function, which then you use as your final output. All right, and again, this seems a little confusing, but just a little tidbit so you understand really what's happening here. Now, I just showed you how to do it with no numbers. All right, So now what happens when there is no number? So to compose two functions without evaluating, you plug in the entire inner function wherever you see x in the outer function. So in this case, remember, I like to think of this. I think of it as g of f of x. All right, so we're starting with f. So we're starting with a f of x, and I'm going to put that in wherever I see x in G. So we're going to have that 2x plus 1 squared, okay, because I'm putting f into G, and then minusing 1. Okay, so again, you can see I'm putting that entire f of x function, that entire 2x plus 1, I'm replacing the x in G with that. Well, now I can't simply leave it like this. So what I'm going to do is I'm going to FOIL this out, because remember, when you have that squared term, really, we're looking at that. And so now you can see, well, really, this can be FOILed. 2x times 2x is 4x squared, plus 2x plus 2x is a plus 4x. Oh, not plus 2, plus 1. And then we still have that minus 1 at the end. 1 minus 1, well, that's just going to cancel off in the end. So really all we have is 4x squared plus 4x. All right, let's take a look at another example. All right, so we have f of g of x. Again, I would always rewrite it like that because I think it makes it a little bit easier to see. We want to take the g function, so the x minus 2. And we're going to replace the x in f with that function. We're putting g of x into f of x. So what does that look like? Well, I have negative 2 times x, but remember, I'm putting g of x in wherever I see x. And now, all I have to do from here is simplify. Well, simplifying in this case means distributing that negative 2 and now combining my like terms. And that would be our new function. But again, the idea is we're putting a function into another function. So let's take a look at where we can actually apply this. So you have a coupon good for $5 off the price of any large pizza. You also get an additional 10% discount on any pizza if you show your student ID. How much more would you pay for large pizza if the cashier applies the coupon first? All right, so this is getting at the idea, which is it better to apply first? Do you want to apply the discount and then the coupon? Or do you want to apply the coupon first and then the discount? And you can actually solve this question by using a composition of functions. So we want to find functions C and D to model the cost of a large pizza. So we're going to let C of x, we're going to let that represent using the coupon. What the coupon will do is it takes the value of the pizza and we take $5 off of that. The discount, what the discount is going to do is it's going to take our pizza, our x, and it's going to take 10% off of x. All right, well, let's think about it. If we're paying 10% less, we're taking off 10%, we're paying for 90% of the pizza. So I'm going to represent that with a 0.9x. Because again, if it's a 10% discount, I'm paying for 90% of my pizza. Well, 90% as a decimal is 0.9. So those are the two things that I can apply to my pizza, the coupon and the discount. And we want to know which is better. So we're going to compare. So first we're going to compose the functions. We're going to apply the discount and then the coupon. So start with the discount. Again, we work inside out like this. So if we're applying the discount first, we start with the discount and then we move outward to the coupon. All right. So applying the discount first. So we take d of x and we're going to put that in wherever we see x in c of x. So that x now becomes 0.9x, and then we have our minus 5. All right, now let's apply it in the opposite direction. So this time we're starting with a coupon, and then we're applying the discount. Well, look at what happens this time. So this time we're putting c of x, we're putting the x minus 5 in for the x of d of x. So we're putting in the x minus 5 in for the x of d of x. Well, now you can see this is getting us a slightly different result when we distribute that. So notice we're getting two different answers. So now this shouldn't surprise us because we saw that in the first example. But let's take a look. Which are you going to end up paying more for? Well, notice when you apply the coupon first, you actually end up getting a less deal. Because notice you're only taking off $4.50 instead of taking off the $5. So let's take a look. If we want to know how much more we would pay, it says, let's subtract this. So again, when subtracting, I'm going to distribute that negative. So you have 0.9x minus 4.5 minus 0.9x plus 5. Those cancel off. Negative 4.5 plus 5. You end up actually paying 50 cents more if you apply the coupon first. And if you think about why that would happen, well, because you're losing part of the discount. Because now you're not getting discounted on that $5 you're going to pay. So by losing the discount on that $5, you end up paying 50 cents more. All right, now I realize this lesson can be kind of a lot to take in because it's very brand new to you. So please make sure, write everything down, then come back to class. We'll make sure to do a couple of examples in class to make sure you're really feeling comfortable with it before I give you your practice work. So again, thank you for joining me, and I will see you for your practice work tomorrow.